Okay, so today I will keep with chapter 2, and first of all I would like to make a bit of a summary of the past lecture. So in the past lecture we were talking about complexifications and real forms. So when you start with an R vector space, you have this way to turn it into a complex vector space. And if you remember, you also had this lemma, which tells you that when you have a R linear map, you can extend it uniquely to a C linear map of the complexification, and this uniqueness turned to be useful. Also, we define what was a real form, which is just a real subspace such that its complexification is the whole C vector space, and the concept of real structure, which is a linear automorphism of the realification of a complex vector space, which is antilinear. It's a C antilinear map, and it's an involution. And more importantly, we proved that there was a one-to-one correspondence between real forms of V and real structures of V. Okay. What else? Yeah, then we were discussing about this homogeneous space, which is the space of real forms of Cn or real structures of Cn. And yeah, we had a bit of a problem with this because yeah. So at the end, I check in Wikipedia that here is complex determinant, I believe, yeah. And yeah, at the end of the day, I talk about this with Ivan, and we didn't discuss the details, but I think we agree that it kind of makes sense, this expression, right, Ivan? Or you have?
I hope. I'll just trust you on this point, really.
Okay, yeah, but according to Wikipedia, yeah, this is the space of real forms of Cn, which are preserving the complex determinant. And here, by preserving the complex determinant, it means preserving the complex determinant by conjugation. Okay, also we define what is a complex structure, the complex conjugate vector space, yeah, and also all these notions that we defined work for Lie algebras, yeah. So yeah, the only one that is a bit different is this one, the complex structure. You have to remember that when you have the complex structure, yeah, if you make J of a bracket, then is X, J, Y, okay? The bracket of X with J, Y. This is what happens if you substitute J by I, okay? So it's natural to impose this definition. And I think that the last proposition that I proved was this one, which says that if you have two real forms of a complex Lie algebra, and you consider the corresponding real structures, then if the real forms are isomorphic as real Lie algebras, it means that the real structures are conjugate by some map of the automorphism group of G. Okay. Yeah, and I also spoke about the quaternionic structures. So it's the same process. If you start with a real vector space, you can complexify it. But if you start with a complex vector space of complex dimension and even number, then you can quaternionify it. I don't know if that works, if that words exist, but yeah. So yeah. Also, I mentioned this relationship between classical symmetric spaces of compact type and these structures that we talked about during the past lecture. And yeah, I think I left it here. And today I will start by telling you about some examples of real forms. So our favorite complex simple algebra is SLNC, right? And also we have a reductive complex algebra, which is GLNC. And I will tell you about the real forms of these two guys, okay? Okay, so this is an example. So first of all, consider this map, which takes a matrix with complex entries of order n, square matrix. So this map is the standard conjugation, okay? And remember that this is a direct product of this one-dimensional complex Lie algebra, abelian complex Lie algebra with SLNC. And sigma is a real structure. Okay, what does it mean to be a real structure? It's a map which has a square identity. So this is easy to check. And it's anti-linear. And yeah, that's basically the definition, right? Or am I forgetting something? I hope not. Yeah. So that's the definition. So yeah, this is a real structure. And now we can look at the set of fixed points of this real structure to see what is the real form associated with this real structure. And these are those matrices which are invariant under complex conjugation. So these are matrices with real entries, right? And if we consider sigma restricted to SLNC, well, sigma restricted to SLNC is again a real structure of SLNC, and the set of fixed points is SLNR. Okay. Second example. Now consider CM, and we are going to choose the standard Hermitian inner product of Cn with signature PQ. So of course P plus Q is equal to N, and H is equal to the following sum. Well, okay, where C, Z, and W are in CM. Okay. Yeah, another way to express this standard Hermitian inner product is like this. You take this matrix PQ, is a m by m matrix, and you perform this operation, okay? You take the transpose of the vector set, and you conjugate the vector W, and you make this multiplication. And IPQ is the matrix, which is, in the first block, is a P by P minus identity matrix, and in this other block is the identity matrix of order cube. Okay? Nice. So now I will consider this group, UPQ. Okay? This is the group, the Lie group, which preserves this form H. Okay? So H of GCGW is equal to H set W for all set and W in CM. Okay. So this is a non-compact Lie group in this case because it has signature. It's non-compact in general. It can be compact if P is equal to N and Q is 0 or the same, or vice versa. Sorry. So now we can compute the Lie algebra of this, which is the set of matrices such that X set W plus H set XW is equal to 0 for all V and W. Okay, this is easy to do. And now, well, using this expression, matricial expression or matrix expression, we can rewrite this as this set, the set of matrices with complex entries, such that X times IPQ plus IPQ times X conjugate transpose is equal to 0. Okay? And you can check that indeed these are the matrices of this form, AV, B complex conjugate transpose, D, and A is in here, and V is in here. Okay. So now, how do I get the real forms or the real structures? Well, I will define the following map, sigma, from GLNC to GLNC, such that for each X, we send it here, minus IPQ X transpose IPQ. Okay, nice. And well, this map, you can check it is a real form, it's C&T linear, it preserves the Lie bracket, and its square is the identity map. Okay, so this is a real form, a real structure, sorry.
Alberto, because of the
Yes.
definition you take before, I think this Lie algebra should be X transpose product with identity PQ plus identity PQ
S conjugate, because you take the definition of the inner product. Maybe they are equivalent, but
sorry, I didn't understand you.
sorry.
Can you repeat again?
Yes. I don't know how to explain well in English, but I will try.
Yeah.
In the definition of the Lie algebra, in the definition of the inner product, yes.
In the inner product, this one.
Yes, in the inner product, you take the transpose in the left.
I take the transpose in the left.
Yes, and this traduced to the Lie algebra, taking the transpose in the left of in the left x. No sé.
Yeah. Okay. So
I think both definitions are equivalent, but.
Yeah, but you mean so you mean that the problem is here in this equality?
Yes.
Okay, but yeah, I thought the same, but there's no problem because when you transpose, you just transpose all, and you can express it like this, okay?
Okay.
Can you see that?
Right. Yeah.
Okay, perfect. Yeah. I thought about that also, but I think it's more convenient to put it like this because then you have this very healthy X without vars and transpose. Yeah, well, it's a matter of taste. Okay. So this is a real structure, right? By looking again to this definition of UPQ, we realize that indeed the set of fixed points of sigma is precisely UPQ. You just look at it and it's obvious that it is the set of fixed points, right? Good. So yeah, these are real forms of GLNC. And now, again, if you restrict sigma to SLNC, and you look for the set of fixed points, you end up with SUPQ, which can be defined as the intersection of UPQ with SLNC. Okay? So they are traceless. Okay, so we already have two examples of real forms. Well, more than that, because these are a lot of them. But there is one more example, which is related with quaternions. So take n equal to 2m now. So yeah, so now if you consider the quaternionic vector space Hm, so this is Q1 to Qm, C1 plus GW1 until Cm plus JWm. Or yeah, am I right? Yeah, I'm right. Okay, so yeah, so now what we are doing is to consider the usual identification with C2M, right? So we put here C1, set 1, set M, W1, WM, and this is in C2M. Okay, so in this way, HM is isomorphic to C2M. And the quaternionic structure, which is given by multiplication of J from the right-hand side, is identified with the following C-linear map, or no, it's not C-linear, right? From the R-linear map, set 1 to set M, W1, Wm of C2M, which takes this into minus W bar 1 minus Wm bar And now it's set 1, set m. Yeah, and I think I have to conjugate here as well. Yeah. Okay. Nice. Okay, so we have the following set GLMH, which is again a subalgebra of GLM2C, a real subalgebra. This is xj equals jx. Okay, these are those matrices. Those matrices in GLM2C satisfying this relation. So in order to get a real structure, we now take the following map from GL to MC to GLM to MC, which is given by X. And now we conjugate by J, right? Okay, so this is again an antilinear homomorphism of Lie algebras, complex Lie algebras, antilinear, is involutive, and then it's a real structure, and the set of fixed points of sigma is equal to GLMH. Okay? And as before, if we restrict sigma to SLM to C, then the set of fixed points of sigma is equal to SLMH, which can be defined as the intersection of GLMH with SL to MC. Okay. So it turns out that these are the real forms of SLNC or GLNC, and there are no more real forms of SLNC. Okay, so far, any question? Are you happy with this? Yes, no? Are you still there?
Yeah, it was great.
Okay, good. So now I'm going to give a result which allow us to establish some correspondence between the Killing form of a complex Lie algebra and the Killing form of a real form of the complex Lie algebra. Okay, so this is the statement. So G is going to be a complex Lie algebra. Now, if G not is a real form of G, then the Killing form of G restricted to G naught is equal to the Killing form of G naught. Okay? Notice that this implies that if G is semisimple, then G naught is semi-simple, right? Because the Killing form will be non-degenerate, and then this should be non-degenerate. So as a consequence, we have that G is semisimple if and only if G naught is semisimple. Good. What else? If now we consider the complex conjugate of G, and we take the Killing form of G bar, then it will be equal to the conjugate of the Killing form of G. Okay? And finally, if sigma is, this implies that the killing form of G, well, is not preserved by sigma, but we have to put here a complex conjugation, okay? So if this is a linear isomorphism of G, then, I mean, linear isomorphism of G as a Lie algebra, then the killing forms are the same, right? But in this case, they differ by by the conjugation, okay? So, proof. 1. So, any basis of G naught is also a basis of G. And now if X is in G naught, we have that add X of G naught falls into G naught. This means that the operator add X, when we look it as an operator of G and as an operator of G naught, is represented by the same matrix. Once we take the same basis, right, of G and G naught, is represented by the same matrix. So this also applies for add X at Y, right? So when we take the trace in G of this will be equal to the trace in G naught of add X at Y, but this is the killing form of G naught, and this is the killing form of G restricted to G naught of XY. Okay, here XY are of course in G naught. So this proves the first statement. Let's go for the second one. I'm going to close the window. So now consider X and Y in G. And add X, add Y from G bar to G bar. This, I told you the other day that when you have a linear map, which goes from G to G, right? And we consider the same map in the complex conjugate version, then when we express this map in terms of a matrix, the corresponding matrix with respect to the same basis will be just the conjugation, will be just the conjugate of the previous matrix. So this can be represented by the conjugate matrix which represents add X, add Y from G to G. So taking traces, we have this. Okay, and last, well, I also told you the other day that yeah, when we have an antilinear isomorphism of a Lie algebra, we can just see it as a automorphism of G just by considering complex conjugation on the domain or in the codomain. So if we look at sigma as a map from G bar to G, this will be linear, C linear, okay? So this is C linear automorphism of the algebras, okay? So in particular, we have that the killing form of G applied on sigma x, sigma y is equal to the killing form on G bar xy. And now using the previous statement, number 2, this is equal to the conjugation. Okay, so we are done. Any questions so far? Are we still there?
Yeah.
Yeah, okay.
Don't worry.
Okay. So, yeah, so we start with semi-simple Lie algebras over R. Yeah, and we have just seen that if we complexify, then we keep obtaining semi-simple Lie algebras over C. Okay, this is a consequence of the first statement. So now we will ask ourselves what happens with simple Lie algebras. Okay, so the question is now start with G simple Lie algebra over R, and now take the complexification. And now my question is this simple? So who believes that this is true? Anybody agrees with this, or?
I disagree.
You disagree because you know the answer. Okay. So somebody want to confront Ivan? Somebody dares? Nobody. Okay. So we will see that this is not true. Okay, this is not true. And we will see when it's true and when it is not true. Okay. Okay, but before moving there, I would like to mention some properties dealing with complexification. So the properties are the following ones. Start, for instance, with a subalgebra in H. Okay, here H, sorry, in G. So here G is a complex Lie algebra, and H is a complex subalgebra or a subalgebra of G. Okay. So yeah, I'm going to change a bit the notation. So instead of considering G a complex Lie algebra, I will consider G a real Lie algebra. Just for a moment, okay? And I will denote by GC a complex, well, the complexification of G. GC is the complexification. Okay, so if you have a subalgebra, a real subalgebra of G, then if you complexify, you obtain a complex subalgebra, HC, and this is a subalgebra of GC. So this is very easy to prove. One just have to look at the expression of the Lie bracket for the complexification. And this is one. So the second one tells us that if H is an ideal of G, then this implies that HC is an ideal of GC. And moreover, if we are on the same situation as above, this means that H is also a subalgebra of G, then this is an if and only if. Okay? Third, now consider just a vector space V in GC. And now, now assume that B has the following form. B is equal to the complexification of some subspace A, where A is a real vector space of G. Just a real vector space. Okay? So now the question is when this happens. When this happens, that for a subspace V, you can find a real vector space A such that its complexification is equal to B. Somebody there to give a condition or? No? Okay, well, so here we have a real Lie algebra, we have the complexification of G. So G is a real form of G, or can be seen as a real form of GC. So what we can do is to define a real structure here. Okay. Which does this job. And here, X and Y are in G. Okay. So we are just conjugating, but we have to take care because this can be done because we already had a real Lie algebra from the beginning. Otherwise, there's not a canonical way to do this. So now, these subspaces V, which are the complexification of some subspace of G, are those which are invariant by sigma. Okay. So this happens if and only if B is invariant under sigma. And in this case, we can also express A as the intersection of B and G. Okay. Nice. Another property for, I don't know what happened. Fourth property, if we start with H, I'm struggling with my screen now. Okay, now it's good. So if H is a subalgebra of GC or an ideal, it doesn't matter, then the image of H under sigma is also a subalgebra or ideal, respectively, of G, of the complexification of G. Okay, and the last thing I would like to mention is the following. If we start with it's just vector spaces of G, then the bracket of A with B, and then we take the complexification is equal to the bracket of A, C, B, C. So we have these properties here. So the proofs of these properties are easy. I don't know if you want to look at some proof. Do you? Or do you think I could skip it, or?
I think it's skippable because it's relatively straightforward.
Yeah, it's relatively straightforward. Yeah, you're right. Okay, so I will keep. So let's move to proposition 3. This is the proposition 3 of the book. I don't know which is the numbering that I am using anymore. So I will call it proposition 3, but it can be whatever. Yeah. So if G is a complex Lie algebra, yeah, then if we consider the realification of G, and now we complexify, this is now isomorphic to G plus G bar. Okay, so now we can look again to this question. So I was asking you if you start with a simple Lie algebra and then you complexify if you get a simple Lie algebra. So this is telling you that the answer is no in general, because if you start from a complex Lie algebra, if it is also a real, well, if you start with a complex simple Lie algebra, it's also a real simple Lie algebra, but when you complexify it again, then you get a sum of two copies. So you get a semi-simple Lie algebra. So what is true is that when you start, if you start with a simple Lie algebra over the real numbers, then you get, after complexifying, a simple complex Lie algebra, a semi-simple complex Lie algebra, but not necessarily simple. Okay. Okay. So
Sorry, can I ask a question?
So can you say again?
Can I ask a question?
Yeah, please.
Is it also true that this G plus G bar will in fact be isomorphic to just G plus G?
No. So because G is never isomorphic to G bar, or I don't know.
But that's not necessary. That's not necessary.
That's not necessary. What do you mean? Sorry.
We can have G plus G bar isomorphic to G plus G. Right, but I mean I think I saw something similar, but I don't quite remember in KNUB. And also another reasoning for this is that if you start with that the isometry group of a compact Lie group is kind of just G times G.
Yeah, you're right.
So
you're right. So yeah, maybe you're right. I am not sure at the moment, but yeah, in general it will not be true. But maybe if you restrict, for instance, to the class of semi-simple Lie algebras, yes, it is true.
Okay.
Yeah, I will talk about this, I think.
Okay, yeah. Thanks.
Okay, but yeah, very good question. Okay, so yeah, how it goes, the proof. Let me look at my notes. No. Here it is. So you define this this Lie algebra, which I call G double because it's the direct sum of G plus G bar. Here G bar is the complex conjugate of G, okay? So now what I'm going to do is to define a real structure of G double, because G double is a complex Lie algebra, right? So I'm going to consider G double, and it's sending xy into y comma x, okay? So y is a real structure. Well, sigma square is equal to the identity, and if you multiply by a complex number, then you, when you take it out, you will get the complex conjugate. So it's antilinear. Why is this? Well, I will just write it down. So take a number, a complex number, C. So remember that when we multiply on G, this is Cx, but when we multiply on G bar, this is C bar Y. And now we have to look at the result of this, which is equal to C bar Y, comma, C X. But this belongs to G, and this belongs to G bar, okay? So when we take the scalar out, from the left entry, it goes a C bar, and from the right entry, it goes also a C bar. So this is C bar by X, okay? So it's antilinear. So sigma is a real structure, and we can look at the associate real form, which is the set of fixed points of sigma, and which is the set of fixed points by sigma, is exactly the diagonal of G double, which I will call G sub D, G diagonal. So this is equal to XX, where X is in G. Okay. So now you consider the following map. Let's call it phi. From GD to GR, okay? This is the realification of G, okay? And the map goes like this. I have XX, and I send it to X. And you can check that this is a homomorphism of real algebras. Yeah, and it extends uniquely to a C-linear isomorphism of the complexification. But what is the complexification of GD? The complexification of GD is G double. Which is equal to G plus G bar. And this is exactly what we wanted to prove. Okay. Nice. So, any questions so far? Yeah. You still there?
I'm still here.
Okay. Good. And now, because I would like to finish for today, I will tell you about this exercise. So this is an exercise from the book, and it tells you that if G is a complex Lie algebra with basis E0, E1, E2, and you have the following bracket relations. You have E0, E1 equal to E1, E0, E2 equal to I, E2, and E1 with E2 is equal to 0. So by linearity, we can extend the bracket. So this defines completely the Lie algebra structure of G. So take this Lie algebra, this complex Lie algebra, and the exercise told us to prove that G possesses no real forms. Okay? So, yeah. So you still there? Yeah. Any idea about the exercise, what to do. I have a solution, but maybe you have another. So we can think about it like 5 minutes, and or maybe less, I don't know. And yeah, and then I will call it for today. But yeah, so any thoughts about this?
Well, we can try to show that the matrix of the killing form cannot be real under no conditions.
Okay. Okay.
Cannot
Very
have real
nice.
entries.
Very nice. Very nice. It's a good idea. I haven't tried this. Look at the killing form and see that there is no three-dimensional subspace such that V restricted to W is real.
Maybe you can do something even simpler. Like you can look at you can take the matrix with respect to this you can take the Gram matrix with respect to E0, E1, E2, and then to find some invariant, which is complex but not real, something like the determinant or the the trace maybe.
The trace. Yeah, but the trace. Yeah. Yeah. But then how do you, sorry, can you say again?
Well, if there exists a real form, then it means that there exists a basis, a C basis for G, such that the matrix of the killing form will be real, will have all entries real.
Yeah.
So if you take any C basis, for example, E0, E1, E2, and write down the Gram matrix of the killing form and find some invariant which it couldn't have.
Yeah,
well, like, for example.
Yeah, sorry.
So like if its trace or determinant, for example, is complex, as a complex number but not real number with respect to some basis, then it definitely cannot have a real form.
Yeah.
So, for example, we can just look at its trace or determinant with respect to these bases E1, E0, E1, E2. It's not sufficient, but if it happens to be complex, any of them, then we're done.
Yeah. We can try that. So yeah, I will look at that. Yeah, that's a good way.
But this is only if we're lucky.
Yeah. Yeah, to be honest, I completely don't know. Yeah. So yeah, do you want me to tell you how to do this, or yeah, a way that I think it works, or you prefer to think about it? What do you prefer?
I would maybe love to try like the idea that I had myself, but then like it may take a bit of time. So maybe I mean you can sure go for it now if you want to explain it, or alternatively you can do it right in the beginning of the next session.
Okay.
I mean you should also ask others.
It was just not to spoil your computation. Okay, so I will just give a sketch. So yeah, so first of all, what kind of Lie algebra is this one? It's not simple, right? Can you see that it's not simple or semi-simple? Can you see that?
It has an ideal.
It has an ideal, yeah.
By E1 and E2.
Yeah, so let's call that ideal V, okay? And now you take G, and you can realize this G as a semi-direct product, right? Can you see that?
Yes.
Yeah. So what's the map phi? So what I'm doing here is just, well, I'm considering this map phi.
Just sends 1 to the matrix 1i on the diagonal.
Yeah, that is. So this goes to the derivations of V, right? Or G, sorry. And now if I have, yeah, let's call this C is spanned by E naught, right? So this goes into add E naught, right? And yeah, and if it's, yeah, and add E naught of E naught is 0, right? Add E naught of E1 is equal to E1, and add E naught of E2 is equal to IE2, okay? Are you still with me?
Mm-hmm.
Yeah. Okay. So now imagine that you have a real form or a real structure, right? So you can check that it lives invariant V, okay? Why is this? Because V is equal to GG, right?
Yes.
So how did you call this? Well, I don't remember how the derive algebra,
Like
right?
the commutator Lie algebra.
Commutator Lie algebra, yeah.
But this is like the complex one, right?
Yeah. Yeah.
So you need to take the C span of all possible brackets.
Yeah.
Okay.
Yeah, so now G is, of course, invariant under sigma. And this is true, right? Because V is equal to G. Okay? So now the hint is to use this fact that that sigma of V must be always be equal to V, and that you have this map phi, and you have to play around with these two, okay? And Yeah, that's what I'm going to tell you. And next day we can keep discussing about this. Are you happy with this or?
Yeah, sure.
Okay. So yeah, so now I have to go. So thank you very much for your attention. And
Thanks a lot.
see you in 2 weeks. Okay.
Okay.
Bye.
Thank you. Bye.